Thank you all for coming today. We are going to be talking about lake houses and warehouses. And there's lots and lots of open source options, so little time, and I think I only have 40 minutes, 30 minutes, something like that. So we're going to try to fit it in 30 minutes or less. So, but the caveat here, I am not going to get to everything. And if you want to call me out for it, go for it. I challenge you. Let's make this a conversation. So what are we going to talk about? We are going to say how to quickly categorize a database. So the reason that I wanted to put together this talk, and I really do appreciate Robert giving me the opportunity, was I get asked all the time, so Rachel, what's the difference between Druid and ClickHouse? Or what's the difference between from MySQL and Mongo? Or, should I use Cassandra for analytics? The amount of times that I answer those questions, I realized that there was a pattern. So what I wanted to do today is talk about how I categorize databases. So how do I quickly figure out what type of database something is and what I should use it for. We're going to go through a very brief history lesson. I promise it won't be, hopefully, not as boring as your US history class, but it will. But hopefully, it'll illuminate what I'm trying to get at. We're going to talk about warehouses. What are they? Why are they? And who are they? Lake houses. They do sound more relaxing than warehouse, but really are they? And we'll talk about that. And then we'll talk about pros and cons, use cases. But first, I'm Rachel. I find that I look much better in drawings than I do in real life. So this is my very favorite drawing of myself. I have spent since 1997 talking about databases. And what do I mean by that? I have been what is called in the industry a sales engineer. And as a sales engineer, our job is to explain to people how a piece of technology works. And the places that I've worked started off with Red Brick back in the 90s. And Red Brick was the first database built for data warehousing by Ralph Kimball. And I've worked for Business Objects. I've worked for Vertica. I've worked for DataStax and then been an evangelist for Cassandra. I've worked for GridGain and so talked about Apache Ignite. I've worked for Imply, where I was in charge of the open source Druid community for quite a while. And now I'm currently running technical services at Ahana, and I'm the outreach chair for the Presto Foundation. So this is my bag. I've been doing this open source database analytics things for a very, very long time. And I'm into open source. So that's me. This is why you should listen to me. But first, I want to make this a little interactive. So go ahead if you want to participate and screenshot the buzzword bingo card here. And you can keep track of what I say, any of these buzzwords, and there'll be a special prize for you at the end. And if you wanted to put in the Q&A that you got bingo, I'm down with that. I think that's cool. Let's see how many of these I get to. But basically this card is pretty much what I'm going to be talking about. How do we disambiguate from all these different technologies? How did they come about? Why did they exist? And I do talk fast. So, also questions. I love questions. And Robert has promised to interrupt me if there's a good one that comes in. So please make this interactive. We're not that big of a group here live in the afternoon. So let's have fun with this. So
I will uphold that promise.
Thank you.
Just make it an interactive.
So this is my #1 cheat code for database serenity. So this is how I make my first determination about what type of databases am I looking at, and how is the data stored on disk. I cannot tell you how important this is, and I actually learned this working with Cassandra and understanding what the file format looked like. And then comparing it to working with Druid and its file format, and then the open file formats like Parquet, like Parquet and Orc and text files. Once you understand how the data is stored and what type of queries you're running, you'll be able to very quickly tell, is this a Is this a database that can handle very small writes very, very rapidly? Or is it one of these things, one of these databases that can scan lots and lots of data over lots of rows or lots of columns? And if you're interested in understanding more about how any of these databases store data on disk, please reach out to me. I'll have my email address at the end of the presentation. Super happy to kind of talk through this. All right, the number 2 cheat code is, very much related, but data modeling. It's a thing. You got to do it. If you don't do it and you don't do it early, it's going to bite you in the butt. So no database is going to be able to fulfill its promise without a proper data model. And how do you do that? You look at the read path. So understand the read path of the database, understand the write path of the database, and then look at your typical queries. And that will tell you how to data model. So between those 2 tips, look at how the data is stored on disk, and then understanding the read, write paths, and what are your typical queries, you should be able to pick which database is the most appropriate for your use case and how to model that for the best possible outcomes. If you don't data model well, you're going to end up having performance problems down the line. I can guarantee you. So let's do a very brief history lesson in pictures. So a long time ago, like the 90s, in a place not so far away from me here in Redwood City, at least, Al Gore invented the internet. And no, the internet wasn't the start of databases. We had databases before. They started off in the 70s. You might have heard the concept of third normal form. Third normal form was a data modeling technique that would minimize the amount of disk used, because back then disk wasn't cheap. So you were trying to minimize the amount of disk that you could use based on the relational databases of the time. There's then another type of data modeling technique called star schemas or snowflakes data modeling came out, and that was designed to make an RDBMS more efficient for running OLAP style queries. And it did mean that you were going to be duplicating data, which meant it was more expensive. So there was a concept called ETL, extract, transform, and load, that would allow you to pick out which data you wanted to use. But anyway, neither here nor there, the internet. Al Gore invented the internet. And unfortunately, what needed this internet to work was databases. So buying people's used stuff or stuff online, or buying pet food, whatever, did require there to be a database sitting behind these web pages. I don't know if you knew, but the database internet grew. And it got really, really, really popular. And there's more and more, if you're my age, you watched a lot of spinning globes and little, hourglasses waiting for web pages to load. And that was because most databases were running on something called Oracle. And Oracle had, yes, there was Informix, and yes, there was DB2, and there was Sybase, and there was lots of other databases out there, but we're gonna talk about Oracle. And Oracle wanted a lot of money to make this internet work. And because databases lived on single servers, if you outgrew your database, you outgrew your server, and then all of a sudden you have to buy a bigger server and more Oracle licenses, and you had to transfer all your data over. And it became very, very difficult for startup companies to create websites and power the internet in a way that was scalable and also performant. So one thing that they started doing is there is a kind of the rise of open source databases. There was this nice little friendly dolphin out there, made lovely little dolphin noises. But this dolphin gave people the ability to run databases and not have to pay the license fees. Not surprising, MySQL ended up being bought by Oracle a few years later. But for the most part, it took some of the stress away of running these databases. So the internet really became able to come off because of these open source relational databases. And of course, there's Postgres, and there's other ones out there too. Then we had St. Jobs of Apple, and he bestowed upon the planet mobile devices. And now we could watch cat videos while standing in lines, and alas, it created a lot more data. So some of the first companies out there to be able to scale to the size of their mobile applications and the proliferation of the internet, companies like Facebook. And what they did is they hired some of the best MySQL engineers on the planet and did what was called sharding. And they sharded MySQL. Basically, they took little tiny MySQLs and put them on small boxes and created one massive database from little tiny bits of the data. Now, the application had to know about this. And so the application needed to know which shard do you need to go to get to your data. But for the most part, it worked. They basically took the dolphin and, put it with thumbtacks and gumdrops and able to create some of the first distributed systems. So this caused what I call the Cambrian explosion of databases. And because there was more application developers, and because application development languages were becoming more and more, more sophisticated, the databases under them didn't need to do as much. So actually, I'm going to go ahead and do this whole thing. The databases were designed for specifically what the application needed. So as we talked about formats, the formats were key value or document stores. They were designed to be able to handle lots and lots of writes, because that's what was bringing down these databases, was tons of people coming to the website or the mobile application, and they have to be able to keep up with that number of writes, but they were small writes. And even the reads back were pretty small, and the reads back were pretty much, on a single partition, or they were on a single row, for lack of a better term. So it was really easy for computers to sit there and say, okay, I need this particular data and I can scan. I don't have to pick up the head. But as soon as you started doing multiple rows, then you started having a lot more latency. But that was okay, because these databases were designed specifically for this. Some of them were also designed to be better for distributing all over the world. So we no longer have the ability, we don't need to shard anymore. They're called transparently sharded databases. They've been stripped of a lot of the transactions property. I do know that Cassandra recently released transactions, but think about how long it took them to put transactions back into what was considered essential for any database of the time. So they took out a lot of those types of pieces and pushed those type of logic to the application. There's also the concept of the cap theorem, where these databases had to choose, like if you have to choose between them, are they consistent, are they available, or are they partition tolerant? And you basically got to pick two. So those were the NoSQL databases. The Cambrian explosion basically came out in order to keep OLTP applications scaling. But we're not at an OLTP conference, are we? We're at an analytics conference. So what was happening on this side of the world? We now have a lot more data. And instead of, and some of the biggest hurdles to being able to analyze data is ETL. Back in the day, I think Gartner said that it took companies 12 to 18 months to build out an enterprise data warehouse, basically build out all the ETL logic required to take all this data from all these different applications and put it into a friendly schema that was able for people to read with all the different data sources. 18 to 24 months, I think it was the quote from Gartner. Now, I want you to think back to what you and your company were doing 24 months ago. Yeah, probably things are different now. Probably things are different than they were 2 weeks ago, to be very honest. But it took too long to be able to manipulate all these data. So Doug Cutting, who I think was here earlier today, and the team decided, hey, let's take this distributed idea and apply it to analytics. So we don't need to bother with as much ETL or that's a typo and thing, or schema on write, let's just give it to the elephant. They'll be able to handle it. So the underlying data got stored in something called HDFS, and then tools and an ecosystem grew up around it to be able to read that data that was stored fairly cheaply. So you could store your data very cheaply. You didn't have to make a lot of decisions up front, and you could still be able to provide analysts with queries. But hey, databases, relational databases can go distributed too, or OLAP ones. So there was a number of different distributed systems like Vertica and Parcel that used columnar formats in order to speed up analytics. So now we're seeing kind of a divergence, right? Instead of using Oracle for all your different workloads and then tuning it differently, you were seeing distributed systems being designed for OLTP, and you were seeing OLAP systems designed for analytics, columnar formats being the most important. And of course, these were all optimized for large batch reads and huge table scans. Columnar formats, of course, are very good at being able to find data very quickly and be able to scan through a lot of data. So, okay, let's go. So what's happened after that? So, we don't see Vertica very much anymore. We don't see Parcel. Where have they gone? Well, the cloud happened. So I would be remiss if I didn't talk about Snowflake. And then there was Redshift and BigQuery. Oh, wait a second. Parcel actually became Redshift. We've gone to the point now where the underlying infrastructure is now being hosted in the cloud, and there is less on the DBA side in terms of managing these databases. So it reduces the total time to value, your total cost of ownership. But as I said, these were mostly designed for batch. They're sort of the next generation from like the Oracles and the Hadoops of the world. I don't know, there's this thing called Kafka. Some of you guys might have heard of it. Streaming and being able to keep up with the ever increasing speed of writes that were happening needed to happen in the OLAP system as well. So this is where you start seeing the ClickHouse, Druids, and the Pinos of the world. And those databases, I think for the most part, and you can correct me if I'm wrong, but I think they're all columnar format, but they also have native support for streaming reads and streaming writes and extremely fast reads. All of them are under a sub-second, and I will not play favorites on terms of which database you should use. So this is where we are, I think, today in terms of the data warehousing market. So we've seen data warehouses grow from Oracle, and then out of the NoSQL systems, distributed databases of the world, you have distributed OLAP systems that are now designed for the cloud and for streaming. And yeah, there's much valuation associated with them too. But let's, actually, I'm going to stop there. I'm going to take a drink of water, and I'm going to stop for questions. Robert, is there anything that's come up?
Hang on one second. I'm just double checking. Let me get don't have one yet. Nope, you're good.
Okay, cool. And I don't hear any bingos yet either. So, all right. So let's break down a database, right? So, now I know this is oversimplifying things, but bear with me. What is the database's function? The database's function is to give users access to data that is stored on disk, right? Yep. Okay. But you need some way for the users to talk to that data. So every application like Excel or PowerPoint, they all have their own way of accessing the data. But in the world of databases, this is typically going to be SQL. Again, we can have arguments about Python and machine learning and all that other stuff, but I think we can all agree SQL is a pretty commonly used way that databases allow users to access data. So now you need some form of abstraction that organizes these files. So SQL is very structured, as in its name, is a structured query language. So it needs to understand the structure of those underlying files that are stored on disk. And ClickHouse, Druid, Vertica, Oracle, all of them, every single database that I've mentioned so far, are all have a proprietary format. So their query engines and their catalogs are all proprietary to the database. So you take the data from any source system and you load it into the database, which then reformats that data into the format that this database can handle. And then it creates what's called metadata tables that allow you to understand or create these logical constructs of tables on top of how these files are stored on disk. And we call those metadata tables. And then you need a system that authenticates users and authorizes them to do stuff. And you take all that together, and let's say that's a data warehouse or a database. For the most part, it's an overly simplistic way of looking at it, but those are the pretty much the basics.
Rachel, can we do have a question that's come up,
Sure.
and it's kind of out of band. Does Rachel have to say the word for it to qualify for bingo, or does it count if it just shows up on a slide? I think that's a great question.
I think it's a great question. I think it shows up on a slide. I think that's fine because it probably meant that I forgot to mention it. I think both. So
great, thank you.
I just need to I'm just making you all do my work for me and make sure that I'm covering all the topics that I wanted to. All right. So then let's take a look at, so what are different ways, I'm trying to introduce a lakehouse concept in the terms of a database, since most people understand databases and lakehouses are newer. So let's take this data that's stored on disk, right? We talked about Hadoop earlier, and that Hadoop was a way of storing a bunch of data cheaply on disk, and then there was tools that allowed you to access that data. So now that same idea can apply to the cloud, but we have new formats like Parquet, or that came out of Orc, and Orc was a Hadoop format that is a columnar structure that is open. So Apache Parquet and Orc are both open formats that allow you to store your data in a columnar way. And you're probably seeing where I'm going with this at this point, right? You're now storing your data in a open format on S3 or MinIO or some type of object store. And we call this a data lake. It could also be called a data swamp, but we're not going to get that. And actually, and there's another thing that I don't have in here, but then on top of these Parquet files, and actually Robert and I were just talking about this, is a construct that's coming out called table formats. Because managing all of those files, one of the things that databases do for you is when you have any inserts or updates or deletes, it keeps those files organized. Now, a data lake is kind of dumb. It doesn't do that for you. So there's concepts called table formats that you can put on top of your data lake that will, more or less, be able to manage inserts, updates, deletes, inserts, updates, and deletes, upserts, whatever you want to call them. So manage those files for you. Those metadata tables, this is where Hive, the Metastore, or something like AWS Glue can come in. So those work really well to create that metadata that translates SQL to the underlying data that are in those Parquet files, for example. We've got open source and cloud versions of the authorization and authentication engines as well. And then the last piece is that SQL query engine. And this is where Presto and its ilk come in. So Presto, Trino, I think the one from Databricks is called Photon. Those are all SQL query engines that allow you to access data that is sitting in open formats. They also allow you to do data federation, so they'll also allow you to query different databases. But we're talking about a lakehouse. So this is pretty much what the SQL Lakehouse is. It's, the Mr. Potato Head of data warehouses, right? Instead of saying, hey, I'm going to be locked into, whatever ClickHouse says the data format should be. I'm going to do it myself. I'm going to use Parquet, and I'm going to use a table format to manage those Parquet files for me. And then I'm going to use Presto, and I'm going to do it all on Amazon. So then I'm going to use Glue as my metadata tables. And you've got this, this really nice, clean, open structure that gives you some of the benefits, and we'll talk a little bit about that fairly shortly, of a database, but without all the overhead. So let's look at some of these storage formats and table formats and query engines. I think I've mentioned most of them, but you can store your data in Parquet or ORC, JSON, CSV. Again, typos. This is what happens when you write your slides the night before. And table formats like Hoodie, Iceberg, Delta Lake. For the most part, each one of those does a really good job of schema evolution. You just need to keep in mind the different features that they expose in terms of functionality. Presto and its ilk, meaning Trino, is the heir apparent to Hive. So what happened there is that Facebook, again, being some of the forefront of these data technologies, was big user of HDFS and Hive, and they wanted to make Hive more SQL friendly, so make SQL the first class citizen rather than MapReduce. So they built out Presto, which is an in-memory SQL engine that can speak directly to the underlying databases or files like in these different storage formats. You might have heard of Dremio. They were based on an open source project at one point called Drill. Photon is another one that comes out of Databricks, and Photon's really interesting because it's a C++ vectorized engine. Oh, no, it's like plus vectorized. It's just a vectorized engine. So it's even pushing this this concept a little bit further. And of course, Presto is not going to sit on its, and Facebook isn't going to sit on its laurels. And so the Presto project and Facebook are working on the VLOX project, which is going to be a C++ vectorized engine of Presto. So you're watching this evolution of going from HDFS and Hive to Presto to a C++ version of Presto. So getting faster, more scalable, easier to use. All right, I'll stop. I think there's Q&A. No more Q&As. Okie dokie. I'm going to go back. All right, so let's look at the pros and cons of all these different things. So why should you warehouse? Well, not surprisingly, warehouses are going to be faster for the most part because everything is interlocked together, and they all work seamlessly. So these are great for analytic applications that require sub-second response. So when you're using your mobile app and there's data that comes to you from your favorite ride-sharing service, lo and behold, that's going to be an analytic engine, right? Because people want sub-second response times for their apps. And you got money, you can get more performance in the cloud, right? So you want to give Amazon and Snowflake a lot of money, you can get really, really good performance out of those systems. Now you don't have to pay for the underlying infrastructure costs, which is great, but they're going to scream at certain sizes. They got their specialized features for different use cases. So you've got lots of different add-ons that allow you to do, really interesting time series types queries, or statistical type of operations, or even specific. I know Druid is working with a format for IP addresses, for example. So, things that are designed specifically to unlock more and more use cases, what you'll see in these warehouses, because they're designed for use cases. You say they're less complicated to manage, especially in the cloud. And you might like to do ETL. But that does mean that the data sets that you're looking at are smaller, they're more curated, because this is all still schema on write. So ETL hasn't gone away. There's a lot more interesting options out there than just Informatica. But for the most part, you're going to be doing you're going to take very smaller, more curated data. Okay, so then when should you use a Lakehouse? One thing I forgot to mention earlier is that data lakes are very well suited for machine learning type of workloads. So you can use Python, you can use PyTorch, you can use all those different tooling out there for machine learning on data that's sitting in a data lake. So it's pretty cool. You've already got your data in a data lake that you're doing machine learning on, and then you just be able to add a SQL layer on top of it. Now you have the ability to give the same data to more and more of your users without any extra cost, because you don't have to duplicate it anywhere. Less vendor lock-in, you have much more choice over where you're going to go. And you can leave your data in situ if you wanted to do federated queries, or if you wanted to leave data in the data lake. So you don't have to move stuff around a lot. It can just sit in the data lake. You can give people access to more data because the data is stored a lot less expensively. There is less need to curate the data. So you can do more like ELT style workloads. You can use larger data sets. It's primarily a schema on read type of approach. And most importantly, you have more control on price and performance. So this is great for dashboards and reports and traditional BI. You don't have to pay to play as much here. Presto and Trino, they have results come back in seconds. We're not in the world of Teradata, where we would sit for hours and wait for it to crunch through its terabyte of data. It's you can do really nice dashboarding with it. Not saying you can't do dashboards with warehouses. We're just talking about the different types of use cases that you might unlock with each different type. But there's definitely room for both of these in most organizations. And that's what is most important, is I see it all the time that people are using both. And why would you use both? We've got this great infrastructure, Kafka or Flink, that you can keep the data from all your different OLTP applications in sync, or send them out to a data lake, and then also send it out to ClickHouse or send it out to Druid to be able to handle different types of applications, because we've gotten to the point now where there is basically a database for every application that you want to build. And it's just a matter, if I want to go back to what I was talking about at the beginning, what is your use case? All right, so I think I'm coming up on time. So in conclusion, you have a lot of options now. You're not just stuck with Oracle or Informix or IBM or whatever. You have lots and lots of options. And you have a lot of options, for, very good architectural and financial reasons. Disk isn't as expensive as it used to be. So we can play around with disk. And now we've got the cloud. We don't have to manage these whole systems on our own. We have learned from history, and systems have evolved since then. So I'm not necessarily saying that Oracle and the older databases are bad. They're great. They handle probably 90% of the world's data workload. But you now have more choices based on the use case. So, choose your workload, understand the underlying data format and the read and write paths of whatever you're looking at. That's, hold on, I don't know if I get to, yeah, there we go. That's super important. Just read and write paths. I can't tell you how many times I was able to figure stuff out just by looking about how the data is stored on disk. So based on number 3, there's no database that can do both OLTP and OLAP at the same time, because science. And I know there was a talk earlier on HTAP, and I'm happy to have that conversation. But my personal opinion, that data is either structured for big reads and big writes, or is structured for small reads and small writes. And anybody who tells you differently is trying to sell you something, or their investors something. What about graph or time series databases? I haven't mentioned any of those. My suggestion to you, look under the hood. Figure out what that time series or that graph database is actually built on. Is it built on a key value store? Then you need to model it like a key value store, and you should expect the performance to reflect how a key value store is going to work. Same with time series databases. So just look under the hood at there's going to be some type of underlying data format. And then choose wisely and data model. Did we get any bingos? I didn't see any. But luckily you're all winners anyway, because you came to my talk. If you want to learn more about Lakehouses, Presto Foundation is offering Presto Con. It's alive and in the Bay Area on December 7th and 8th. Feel free to sign up. And because you came to my talk, you get a coupon for 75% off of Presto Con. Should be a really great event. We've got some really cool database optimizer talks and other really deeply technical things. And then we also have a lot of Lakehouse. So all those Lakehouse technologies that I put on the board earlier are all going to be representative and be able to talk about the different pieces. So if you're at all interested in Lakehouses, PrestoCon has a definite Lakehouse bent. So Lakehouse and analytics. And that's it. 2 minutes. 2 minutes for questions.
Thanks. Any questions? And while we're waiting for folks to type stuff in, Rachel, have you tried Photon?
I have not personally, no. I'm more new to the Lakehouse side of the equation in the last few months.
Yeah, because I think that's been one of the more interesting developments this year.
Oh, for sure. I mean, I'm
more
involved in VLOX, which is probably even better than Photon. So take a look at the VLOX stuff too.
Right, and what is VLOX? So, oh, here we go. Yeah, can you elaborate a little more on why you think there's such a strong trade-off between OLTP and OLAP? It seems intuitive, but is there some fundamental limit here that's impossible to work around?
Yeah, and again, I think it comes down to the. All right, so let's think about data that you. I mean, again, SSDs are going to be a little bit different, but if you just think of the way that a disk is written to or it gets read from, right? You've got a head and the disk spins, and it only can spin so fast, and otherwise there's going to be a mini sonic boom. So what you want to do anytime you retrieve data from disk is put the head down and scan. You don't want that head to come up and down a lot. That causes IO, and that is what's going to kill your latency if you have to jump around that disk. And that's why I think that the data modeling and the data format on disk is so essential, because at the end of the day, that disk can only spin so fast, and you only want that head to only be able to move around so much. Now, SSDs do help some of this, but for the most part, it's going to be the same thing. Which blocks are being read in which order, and moving around a lot on disk to be able to find different places isn't going to make your queries fast. So if you are doing if you're doing very short reads, you just go in and out super fast. If you're doing very long reads, you want to be able to put that head down and read for a very, very long time. That's what I say. That's the physics behind it that I see. And you can put a lot of lipstick on a pig, right? You can make this a lot better, at the higher levels, but fundamentally, just like, the speed of light is a thing, same as, rotational velocity.
Okay, any more questions? I hope other people got bingo. I got bingo. There were enough words mentioned here. So here we can hold for another minute, see if there's any other questions, and meanwhile, thank you very much, Rachel. Really appreciate the talk.
You are very welcome. Thank you for having me.
Yeah, no, it's been a pleasure. So good. I think we will call it good. We've got a couple more talks coming up. enjoy the rest of the conference. I hope the talks have been fun, and we will see you soon. Thanks again, Rachel. Talk to you soon.